Hi, in today's video I would like to show you a very small demo written in BASIC. It's very similar to the demo that I showed you in my previous video, but it uses completely different technique and it has much nicer code, well, at least to me personally. It's only 2 lines of basic code, so yeah, let me show you and then we will talk a little bit about that technique. So a load chain. Yep, so let's run it. So it's simple endless chain, except for this. And then it goes on and on, of course. So let me show you the code. Yeah, just 2 lines of code, a little bit of peeks and pokes, and that's about it. Doesn't use any sys commands or anything like that, so it's pure basic. I have a couple more demos to show you, and then we can explore the code together and see what is this technique about. So yeah, let's load. Let me see what else do I have here. Yes, I have Christmas tree. We have Christmas tree, of course. Let's load Christmas tree, because why not? Oh, it's green. There you go. So this demo is all about creating this colors going upwards. Like I mentioned before, it's very similar to the demo that I did in my previous video, except it uses completely different technique, and this is the part of the code that I will explain how it actually works. Yeah, so one more demo. Let's load X. Ah, okay, now let's take a look at the code. Let me load that first demo again. So let's just run it to see. Yeah, that's the one. So let's list the code. Yeah, like I mentioned before, there's only 2 lines of code, and the first line, this line number 0, actually just create that endless chain, which is not really important for our discussion today. Also, these 2 next commands are part of that first line, line number 0. That's something that we are going to remove from the discussion. So let me remove these 2 next lines, and also I need to 53210.0 and go to 0. So this go-to command just jumps back to the line 0, so we are going over and over again. We don't need that for our discussion. Poke 53281 is actually just color, background color. We are setting the background color to black after first iteration. Yeah, not really important for this as well. So yeah, let me show you what we are left with. So let's list line number 1, and this is our code that we're going to talk today, and this is the part of the code which generates those colorful bars. So yeah, Let me break this a little bit further into a couple of lines. So line number 1 will be this poke 648, 16. Then let's say at line number 2 we have this for loop for I equals, now dot is actually represents 0 to 100. Line 3 is poke 646, comma peak 162. Then we have simple print command without actually printing anything. Then line number 5 we are closing the for loop with next command, and line number 6 is our poke, again 648 register, and this time we are poking value 4. So yeah, this is the part of the code that we are going to discuss, and I will explain what the hell is going on here. So the main part of this whole code, or this whole demo, is this poke at line number 1, which says poke at memory address 648, and we are poking the value 16. And the last line we are poking again at that same memory address again, but this time value 4. So let's see what this 648 memory address actually is. So at memory address 648 there is a value, of course, which tells the kernel where the screen memory is located in the RAM of Commodore 64. So this is actually pointer to screen memory, and this is pointer vector. Like I mentioned before, it's for the kernel. So the kernel uses this value at this memory address to find the location of text screen in RAM of Commodore 64. And besides the kernel, we have VIC-2 chip, which actually has his own vector pointers to the screen memory into Commodore 64 RAM. This is often used in games, of course, so we can shift quickly between the different screens. But the kernel uses this just when we want to print something on the screen, so that the kernel knows where to write these values that we are going to print. So if we just say print A, well, this A appears right here because the kernel knows where the text screen is located in memory. So let's see what value currently by default has this memory address. So if we print peak at memory address 648, and let's see what value will came up, and as you see the value is 4, and you can notice that I used that same value at line number 6. That means that we changed this value at the beginning, then we did some for loop doing stuff, and then we return back to the default value. So the kernel has his own memory register to tell him where the screen is located in the memory of Commodore 64. VIC-2 has his own register, and these two things are not connected, and they are not necessarily synced. So that means that we can have kernel printing in one part of the memory of Commodore 64, while VIC-2 chip displaying completely other part of memory 64 as the screen that is going to be displayed on video output. So this technique is actually used here. We are telling the kernel to print something somewhere else, while the VIC-2 is still pointing at the default memory location in the RAM of Commodore 64, showing our default screen as it is. Now, if you think about it, this whole code doesn't really make any sense. We're telling the kernel that the screen is at different memory location, starts at different memory location. We are printing at line 4 absolutely nothing. Well, this prints nothing and jumps to the next line, so we are constantly creating new line, new line, new line. But these prints are not shown anywhere. We cannot see it because VIC2 chip displays completely different screen. So all of this makes no sense, except this line number 3, which is kind of strange, which actually pokes at memory address 646 the value from memory address 162. Now, what the hell is this? Well, there is one thing that we cannot change in Commodore 64, and that's the location of color RAM. It's always at the same location. It starts at the D8000 hex and ends up 1000 memory location later. Whatever we do with the kernel pointers or VIC2 pointers or whatever we want to do, we can change it except for the color RAM. It's always there. So memory address 646 is the address where we store the color code for the text that you're going to print on the screen, or we're going to type in, well, whatever. When the cursor moves on the screen, it uses the color that code is stored in this memory address. So we're constantly changing this, and we're using the value from memory address 162. The memory address 162 is part of the TI variable, which represents the number of jiffys, and this is the lowest byte from this number. TI number is 24-bit number, so it contains, it's constructed from 3 bytes, and we are taking the lowest byte, the value from that lowest byte, to peek into our memory address 646. So here I intentionally use the TI variable because that lowest byte is quite repetitive. It changes very fast, and the basic code is slow enough to get different value every time. But again, these values are not purely random. They have like a pattern of repetition, which is very nice to see when we are changing those colors, and you can see the group of colors repeating and traveling upwards, right? So that's the reason why we are doing this. Now, again, how all of this actually works. Well, let's start from line number 1. We change the pointer for our kernel to use different parts of the memory of Commodore 64 as the screen memory, right? And we are looping 100 times. We are changing the text color, and then we are using print. So print means that we are going to jump to the next line. Where we reach the end of the screen, of course, the Commodore 64 or the kernel will start to scroll the screen upwards. What that means, besides scrolling text or whatever it is on the screen, it will also scroll the color memory. Let me explain this. So if I use, so we have like pink kernel, and then we have green VIC2, and let's say that we have like yellow C64, right? So each of these lines has its own color. So if we go forward or create new lines, you see our text is moving upwards, but also the color has to remain the same where we defined it. So that means that values in color RAM needs to be scrolled as well. And this is exactly what we are doing here in our demo. So we are just generating new line and new line, and as you can see, our colors are moving upwards, but we changed the kernel pointer for the screen memory location, but we didn't tell the VIC2 chip to do the same. So that means that VIC2 chip doesn't see our changes or our prints that we are doing, but again, it sees the color because the color RAM is always at the same location. this is how this demo actually works. We are changing the color, we are printing, so we are generating a new line for each iteration. And then once we are done, we are going back to the default screen vector. When we jump back to the line number 0 and we are again printing something or generating that chain, it's again visible on the screen. So, okay, let's try to run this code now and you will see what will happen. You see? So we are changing the color, printing or creating new line in each iteration, and as you can see, the text on the screen or any character on the screen gets affected by it, and that's our little demo, and we can run it again. So what I didn't explain is what these values actually means when we are poking them into memory register 648. So we have 16 here and we have 4 here, and as you saw before, the 4 is the default. So if I peek again at 648, we will get 4. So obviously 4 is the default. So this value represents the most significant 8 bits or high byte for our vector. So that means that we need to multiply this number with 256 to get absolute memory location for our screen memory, or better say text screen memory. So in case of default, we need to multiply number 4 with 256. So let's multiply 4 with 256, and of course you will get 1024, which is default memory location where the screen is located on Commodore 64. So what's happening here with this 16, where that goes? So let's check that as well. So 16 multiplies by 256 will get us to 4096. Now 4096 is one of the available locations for the screen memory for the VIC-2 chip. So yeah, we are not doing anything harmless. We are just pointing the kernel to write at one of the available memory locations where the screen can actually be located, well, at least considering the VIC-2 chip. So yeah, it's perfectly safe, perfectly fine. Just we don't tell the VIC-2 chip that our screen location is moved to different location. So yeah, that's our little demo. I do like that X demo, which is kind of really cool. Let's list it. Again, 2 lines of code, and again, first line just generates that 2 beams crossing in the middle of the screen, just that X. And again, except for these 2 next commands, everything else here is the same as I explained it before. So I'm using the inverted space, which is this Petsky character, and again, because these are the characters that are going to be affected by changing color, yeah, you can see that. So the only downside of this demo, or every demo, if you break the code while we are doing this, so let's say I hit break and there is nothing here. Well, it is. It just, well, the vector pointer for the screen memory location is changed, right? It's not there. VIC-2 chip doesn't see it. So we need to go back to default. So in this case, because this code runs to infinity while changing the colors to infinity, there is no end for in this demo. So I need to poke that memory address 648 with value 4, and I need to type that in without actually seeing what I'm doing. So poke 648 comma 4, and we have our ready prompt back. Yeah, or you can just reset your Commodore 64. Nevertheless, I like this. This is all that I have for you today in this first video in 2025, and until next time, goodbye.